Okay, so previously in the example, what we have done is just that we know the feed flow rate and the solvent flow rate, and we know the compositions of the feed and the solvent, and we know that the specified composition of the final raffinate phase. So then we work out to find out what is the composition in the extract phase and what is the final composition in the raffinate phase for the solvent, and we work out the flow rate using the overall and component balance. But we haven't yet determined the number of stages required to reach the LN, to reach the desired raffinate specification. So now we're going to determine the concentration at each stage and the total number of stages N to reach the LN, the specified composition for LN. So okay, so let's look at the diagram here for the multiple stage LLE process. So let's say you have 1, 2, 3, 4, 5 until n number of stages. Let's have a look at the stage 1, total balance on stage 1, input equals to output. So for stage 1 here, just look at the stage 1 as the control volume. So input equals to output. Input is L0 plus V2. Output equals to L1 plus V1. Then, if you repeat the same thing for stage 2, so for stage 2, you have input is L1 plus V3 equal to L2 plus V2. Okay, let's say if you add another stage here, number 3, then you have in is L2, and then you have here V4, and then here you have L3. Okay, so for stage 3, let's say if you want to, I just want to show you the process of deriving the equations here. So for stage 3, input equals to L2 plus V4 equal to output is L3 plus V3. And if you do for stage N here, so I'm just going to delete this stage 3 and just focus on stage N for the time being. So for stage N, input is L sub N minus 1 plus V sub N plus 1 equals to L sub N plus V sub N. And then if we want to rearrange from equation 12.5 here for stage 1, so from equation 12.5 stage 1, you can rearrange this equation to get L0 minus V1 equal to L1 minus V2. And from this stage 2 here, you can also rearrange L1 minus V2 equals to L2 minus V3. And from stage 3 here, you can rearrange also L2 minus V3 equals to L3 minus V4. Okay. Okay. So you see the pattern here. So here is okay, here is L1 minus V2. L1 minus V2 is also equal to L2 minus V3, and L2 minus V3 is also equal to L3 minus V4. And if you repeat the same step until you reach the total number of stages N, you shall get something like this, something like equation 12.6 show. So what this means is that so L1 minus V2 equals to L2 minus V3 equals to L3 minus V4, and so on and so on. It means that this is delta equals to this delta equals to this delta here. So the delta, the difference in the flow rate of L0 and V1, okay, the difference in the flow rate of L0 and V1 equals to the difference in the flow rate of L1 and V2 and L2 and V3, and so on and so on. It's a constant for all stages. It's a constant. So this is for the total flow rate of liquid and I mean for the solvent and feed flow rates, because we don't have a vapor flow rate here. Okay, so V is the solvent phase and L is the carrier phase. So this also holds for component balance on component A, component B, or component C. So if you do for the component A, let's say, so the difference in the flow rate of component A equals to L0 XA0 and V1 YA1 equals to so on and so on until you reach the stage N. So what is this saying is that we are focusing on the delta here. Okay, we are focusing which is a constant. So if you combine the equations 12.8 and 12.9, and if you solve for only the x delta, meaning the change in the flow rate for the component, you should get the x, the value of x. Here x is the coordinate for the point delta, okay? So meaning if you, let's say you do the component balance of component A, then you get x delta for A. And then if you do the component balance for component B, you shall get x delta for C. So if you get what is the x delta A and what is the x delta C, you get the coordinate of the point delta. So the point delta here, the coordinate is not confined to values between 0 to 1. No, it's not confined with that value. It can be negative, it can be more than 1, because it's just the location of your operating point. So the delta here is the operating point because the delta here is a constant throughout all streams passing each stage, and it's like a common point that every stage will pass through. So it is known as the operating point. This operating point is important to get the number of stages. Okay. Okay, so next stage is after we know how to determine the operating point, we will use that to calculate the number of stages in countercurrent liquid-liquid extraction. So there are three methods to get the number of stages in the countercurrent LLE. One is using the Hunter-Nash method, that is using the equilateral triangular diagram. Or we can use the rectangular coordinates, i.e. the right angle triangle, and we will use this primarily. And finally, we can also adapt the McCabe-Thiele method, similar to the distillation and absorption stripping process, where you have equilibrium line and also operating line, but we will do this for dilute and immiscible solutions. So let's straight away do an example to show you how to determine the number of stages. So here we are using the same system, i.e. the acetic acid, water and isopropyl ether system. So you have a pure isopropyl ether at 450 kg per hour being used to extract an aqueous solution of 150 kg per hour with the acetic acid concentration component A is equal to 38% using countercurrent multistage extraction. Your exit concentration in the aqueous phase of the acid is equal to 10%. So calculate the number of stages required given the LLE data. So here in the graph here, I have shown you how to, the plotted equilibrium line, and then you can plot already the known points, which are Vn plus 1, because it's a pure solvent, it's 0, 1. And then you can plot also the L0, the feed concentration, 0.3 and 0. And you have to calculate the point M. So you can calculate the point M, XAM equals to 150 times 0.3 plus 0 over 150 plus 450. You get 0.075, and XCM equals to 0 plus 450 times 1 divided by 150 plus 450, you get 0.75. So the coordinate AM is 0.075 and 0.75. And also you can plot the location of LN, because you know your final raffinate phase is, you want the XAN to be equals to 0.1. So you get the XCN here. So this is your point LN. So you know that if you connect the point LN and point M, you shall get the point V1, because LN, M and V1 should all lie on the same line. So you can try to plot here. Okay. So here is your point V1, And also, if you want to just satisfy yourself, you can try to plot the point Vn plus 1 m and L naught. It should lie on the same line, okay? But it's not necessary for now. So here you have plotted L1, Ln, V1, and everything else. So what we want to know what is the value of n. Okay, so 1, 2, we don't know until how many stages? N. So here is L naught, here is Vn plus 1, here is Ln, here is V1. Okay, so here I just want to reiterate that V1 is not in equilibrium with Ln, rather V1 is in equilibrium with L1. Then here is L2, so L2 will be in equilibrium with V2. So the ones that will lie on the tie line are the points of V1 and L1 will lie on the same tie line. V2 and L2 will lie on the same tie line. And V3 and L3, if you have stage number 3 here, it will lie on the same tie line. Okay? Okay, let's recap. This here is the point M, this here is point Vn plus 1, here is point L naught, and you can plot the point Ln because here is where xan equals to 0.1. So here is your point Ln. So next is you can locate point V1 by connecting the point L0 and point M together. Bear with me. I'm trying. I'm sorry. Try again. Just draw. Okay. So here is V1. Okay, I'm just illustrating how to do it, but you better do it on your own properly on paper. Okay, so here is your point V1. So now we're going to use the operating point. So operating point delta equals to L0 minus V1 equals to L1 minus V2 equals to blah 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 until Ln minus Vn plus 1. Okay, so we're going to connect the points L0 and V1. Okay, L0 and V1 you connect. Okay, and then if you connect point Ln and Vn plus 1, okay, so you get the intersection between the the lines Ln and Vn plus 1 and the L0 and V1, you shall get the point delta. That intersection between the two lines give you the delta. So this is V1. So you know V1 is in equilibrium with L1 and they must lie on the tie line. But here V1 does not fall onto any tie line, but you can approximate a tie line passing through V1 by looking at the two tie lines nearby. So what you do is you approximate a tie line. Okay, then you can get L1 here. So that is L1. So meaning here for stage 1, this is L0, this is V1, then you get L1 line. Okay, then go to stage number 2. Stage number 2 you get V2. Then you get here L2. You just want to know how many times you have to do this until you reach Ln. Okay, so from L1, you want to find V2. So you know here from the operating point L1 minus V2, you can use the operating point now that you already know the operating point. So what you do is you connect L1 and the operating point to get the V2. Okay, so you draw a line, straight line ideally, passing through L1 and touching the operating point, you get here V2. Okay, here is V2. Then V2 is in equilibrium with L2. Then you draw a tie line that passes through V2, and that will give you L2. Okay, so then L2, you repeat the same step. After you get L2 minus V3 equal to the delta, right? So you approximate another tie line. You draw another line between L2 and the point operating point. Then you get here V3. Okay, so you get V3. Okay, so then you get here number 3, V3. Okay, so and then after V3, you approximate another tie line to get the L3. After you get L3, you repeat lah. You connect L3 and the operating point. Okay, and then I think all we need here is the 3 stages, L3 and V4. So all in all, approximately for this problem, you repeat the process until you have to stop at nearby Ln. So I would answer this such that we need about 3 stages. Sometimes you can reach up to 2.5 stages or 4 stages, depending on how many times do you have to do the repetition. Or alternatively, you can calculate how many teeth do you have. In this case, this is 1 teeth, okay, teeth. And then 2 teeth and 3 teeth. Meaning, but in other words, you do this, how many times you have to repeat it, and that is the number of stages required for you to reach the Ln here. Okay, because you want to repeat the same process until you have to stop at xan equals to the desired specification. In this case, xan equals to 0.1. Okay, after we have learned how to determine the number of stages for multiple LLE, now next stage is to determine the minimum solvent flow rate. Just like what we did in absorption, in stripping, in distillation column, there must be some limiting cases. For absorption, the limiting case is the minimum liquid flow rate. For stripping, the limiting case is the minimum vapor flow rate or gas flow rate. And in distillation, the limiting case is R min or N min. So for LLE, the limiting case is the solvent flow rate. If the solvent flow rate Vn plus 1 is too low, then you cannot do the separation. Maybe if you choose the minimum solvent flow rate, then you will have to deal with infinite number of stages, because the operating line, the operating point will go through the delta. It will cross through the tie line. So that will give you the minimum solvent flow rate, because here in dealing with equilibrium data, you have to know that limiting case is when the operating point or operating line reaches the equilibrium line. So now for actual operation, for actual solvent flow rate, we need to multiply with how many times the minimum solvent flow rate. For example, just like in absorption and stripping, if you have found out the minimum gas or liquid flow rate, then the actual flow rate, then you have to times 1.2, 1.5 to get the optimum flow rates. Okay, so now here we want to determine the minimum solvent flow rate. We need to use the triangular phase diagram. We can either use equilateral or right angle, but I think it's more practical to use the right angle triangle diagram. Okay, so let's straight away go to example to Determine the minimum solvent flow rate. So in this example, an aqueous feed solution of 1000 kg per hour containing 23.5% acetone and 76.5% water is being extracted in a counter current multi-stage extraction using pure methyl isobutyl ketone solvent. The outlet water raffinate will contain 2.5 weight percent acetone. Calculate the minimum solvent that can be used and calculate the number of theoretical stages for a solvent flow rate of 1.5 times the minimum solvent flow rate. So here your LLE data is different from what you have seen for the acetic acid, isopropyl ether and water system. But you have seen this kind of equilibrium data in the previous lecture. So you can refer to that lecture if you want to know how to plot the equilibrium curve. So in this example, it's a bit tricky. Okay, let's draw first. Okay, you have one stage, two stages. You don't know actually how many stages do you have. So until n number of stages. So you have L0 here, Vn plus 1 here, Ln here, and V1 here. All you know is the L0 equals to 1000 kg per hour with XA0 equals to 0.235 and XC0 equals to 0. And Vn plus 1, you know YAn plus 1 equals to 0 because it's pure solvent. So YCn plus 1 equals to 1. And your desired specification for the raffinate phase is XAN equals to 0.025. But you don't know the flow rate for Vn plus 1. So you don't know, when you don't know the flow rate of Vn plus 1, you cannot calculate the M point. Okay, when you cannot calculate the M point, you cannot calculate the number of stages. So in this case, we need to find the Vn plus 1 minimum. That's what we want to find. So first of all, we plot the known points, which are, although we don't know the Vn plus 1 flow rate, but we do know the coordinate because of the 0 and 1 here. So you plot here Vn plus 1, and you also know L0 coordinate, 0.235 of XA0. So here is your L0. And you also know Ln, your desired specification is that XAN is 0.025. So you can plot 0.025 somewhere here, 0.25, okay, maybe somewhere here. Wait, this is 0.05, so 0.025 should be somewhere there. Okay, so this is your point Ln. Okay, let's erase this first. Okay, so the limiting case is when the operating point passes through a tie line. Okay, and we don't know V1 because we don't know M. So we have to approximate a tie line that passes through L0. Because to get the operating point, so operating point is L0 minus V1 equals to L1 minus V2 equals to blah blah until Nn minus Vn plus 1. So here we want to know the minimum Vn plus 1. Okay, so we have to get Vn plus 1 minimum, it's when the operating point passes through the tie line. So you can draw your actual tie line using your graph paper. Okay, but it's too small for me to properly draw a tie line here, so I'm just going to approximate a tie line, how it looks. Okay, so from the equilibrium data, the tie line passing through L0 should look something like this. Okay, so I'm approximating, so I'm just drawing extra. So this one is V1 at Vn plus 1 minimum. Okay, then the next thing is to get the operating point is also equal to Ln minus Vn plus 1. So what I do is I connect the points Ln and Vn plus 1. So I connect these two lines, I mean 2 points, and extend it such that I can get this delta at Vn plus 1 minimum or delta minimum. And then because L naught and Vn plus 1 minimum and M minimum at Vn plus 1 minimum should lie on one line, and also Ln and V1 minimum and M minimum should also lie at one line. So let's connect the lines. So here L naught and also Ln to V1. Then I get this point M at Vn plus 1 minimum. So what I do now is that I can get the coordinate of XAM at minimum Vn plus 1, and also I can get the XCM coordinate at Vn plus 1 minimum. Then I can use material balance to get Vn plus 1 minimum. Okay, so the original equation for XAM is L naught XA naught plus Vn plus 1 YAN plus 1 over L naught plus Vn plus 1. So at Vn plus 1 minimum, it's XAM minimum at minimum equal to L naught XA naught plus Vn plus 1 YAN plus 1, this one is minimum, over L naught plus Vn plus 1 minimum. But if we are using pure solvent, then YAN plus 1 will just be equal to 0. Then if I can read the value of XAM at minimum Vn plus 1, I know this, and I know this, I know this, I know this. The only thing I don't know is Vn plus 1 minimum, so I can rearrange this equation to actually get the minimum flow rate for solvent. Okay? So going back to our example just now, if you properly do the tie line, and the equilibrium curve, you get XAM at Vn plus 1 minimum equal to 0.175 from the graph. So you can calculate the Vn plus 1 minimum. 0.175 equals to L naught, i.e. 1000, XA naught 0.3235 plus Vn plus 1 minimum times 0, because it's pure solvent, so there's no A in the pure solvent, and then 1000 L naught plus Vn plus 1 minimum. Then you can solve for Vn plus 1 minimum. From here you can get the Vn plus 1 minimum equal to 340 kilogram per hour. So next, for question B, is to calculate the number of stages, find N if Vn plus 1 equal to 1.5 times Vn plus 1 minimum. So here, this one is quite straightforward. You can calculate the Vn plus 1 first. So Vn plus 1 equal to 1.5 times 340 equal to 550 kg per hour. So we'll continue to solve for question B. Alright, now for question B. For question B, you can straight away try to calculate the XAM and XCM. So XAM equals to L naught, XA naught plus Vn plus 1, YAN plus 1 over L naught plus Vn plus 1. So here 1000 times 0.235 plus 510 times 0 over 1000 plus 510. You get XAM equal to 0.156, XCM equal to 1000 times 0 plus 510 times 1 over 1510 equals to 0.337. So this one you can plot on the graph. So here is XCYC, no, YAY, yeah, XCYC. This is component C, this is component A. So if you have this diagram, so you can plot the point M somewhere here maybe. So this is point M. Here is Tn plus 1. Somewhere will be L naught. Then you can plot your Ln. Then you can start doing the stepping of the stages as what we have shown in the previous example. So you can try to do this. Connect Ln and M to get V1. Then you connect V1 and L0. And then you connect Vn plus 1 and Ln until it intersects to an operating point. And then you try to draw a tie line to get L1. And then from L1, you draw with operating point to get another point V2. Then you draw another tie line to get L2. Then from L2, you connect to get V3. Then draw another tie line until you repeat the same step until you finish to Ln. But in this particular example, the final answer is about 5 stages. Okay, so this one I think you can try to do on your own. I don't want to bore you with the details. You know the steps: find M, locate V1, and then connect L0 and V1 to get the delta, and from the delta, and then connect Ln and Vn plus 1 to get the delta, and from the delta you can step up the stages and calculate how many times you have to do that until you reach the desired Ln. So in this case it's 5 stages. Alright, so next one is if you are doing extraction with immiscible liquids, if the solvent stream contains components A and C and the feed stream contains the component A and B, and that components B and C are relatively immiscible in each other, the stage calculation can be done more easily. So now here the solute is A, the solvent is C, and the carrier is B as before, and that the components B and C are immiscible and it's dilute. I mean, if the solute A is very dilute, then we are transferring the solute A from the L phase to the B phase, from the carrier phase to the solvent phase. Then the operating line will be straight, and it's easier to use McCabe-Taylor diagram and or Kramser equation to calculate the number of stage. And if you remember the operating line equations for absorption and stripping as shown in the equation here, and then so this here is the operating line for the whole column for n, capital N number of stages, and the bottom equation is if you are doing the equation to get the intermediate points for the operating line somewhere in the middle of the column, if you can recall this equation. So let's do an example for extraction with immiscible liquid. In this example, an inlet water solution of 100 kg per hour containing 0.01 mass fraction of nicotine in water is stripped with a kerosene stream of 200 kg per hour containing 0.0005 mass fraction nicotine in countercurrent stage tower. The water and kerosene are essentially immiscible. It is desired to reduce the concentration of the exit water to 0.0010 mass fraction of nicotine. So you are asked to determine the theoretical number of stages needed. Equilibrium data is given here, where X is the mass fraction of nicotine in the water phase and Y is the mass fraction of nicotine in the kerosene. So here the given values are L0 equals to 100 kg per hour, X0 is 0.010, X0 here is just XA0, okay, Vn plus 1 equals to 200 kg per hour, and Yn plus 1 equals to 0.0005, and Xn is 0.0010. So you can calculate the inert streams. The L prime equals to L times 1 minus X equals to L naught times 1 minus X naught equals to 100 times 1 minus 0.0005 010, so you have 99.0 kg per hour of water, and the V prime equals to V times 1 minus Y equals to Vn plus 1 times 1 minus Yn plus 1 equals to 200 times 1 minus 0.0005. You have 199.9 kg per hour of kerosene. So you can make an overall balance on A and solve for the Y1, and you get Y1 equal to 0.00497, and then you can plot the operating line, because you can plot the operating line to be a straight line because this is a very dilute solution. Okay, let's just recap the tower notation. So you have V n plus 1, so Y n plus 1 here is 0.0005. Here you have Ln, so Xn here is 0.0010. Here you have L0 and X0, 0.010. Here you have L1 and X1. I mean V1 and Y1, sorry. So here is V1 and Y1. So Y1 is 0.00497. You can do a material balance. So these are your coordinates for the operating point, and as the solution are very dilute, you can expect a straight line for the operating line, and you are also given the equilibrium curve, so you can plot the equilibrium curve. So if you plot the equilibrium line, you get the blue line, and if you plot the operating line, you get the orange line. So here is your X0 and the Y1, and here is your Xn and your Yn plus 1. Okay, so then you can step up the stages. In this case, I've already stepped up the stages for 1, 2, 3, 4, about 4.5 stages. Or you can also use Kramser equation if you want. You can still the A equals to L over mv. Just have to locate whether the operating line is above or below the equilibrium line. In this case, it's below the equilibrium line, so then you can decide whether to use the absorption or stripping equation for the Kramser equation. Finally, you can also use the things that you have learned to design packed towers in absorption and stripping. You can use the same concept to design extraction column using the mass transfer coefficient. It's the same. It's just that now you just have to identify which one is the L phase and which one is the V phase. Okay. For extraction, for example, if you use HOL and NOL, and if the operating line and equilibrium lines are straight and dilute, you can simplify the equations as you can see here. In terms of the V phase, if depending on where your resistance in mass transfer is mainly occurring, whether in the L phase or in the V phase, then you should decide whether to use NOL or NOV. So if previously in absorption you use NOL or NOG to indicate the liquid and gas phase, but here use NOL or NOV to liquid the L and V phase. So normally V is the solvent phase and L is the carrier phase. So either things are the same. As I said, you have to identify whether your solute is transferring from the L phase to the V phase or from the V to L phase. Then you can just modify the type of equations that you use to adapt to the LLE process. So that's all for our lectures on the multiple stages LLE, and that's the end of our separation processes 1 course.